Okay, let's take a look at homework number 23, which had to do with moments of inertia. The first one says find the moment of inertia and radius of gyration with respect to the y-axis. Now this is just like one from the notes, if you took a look at those, except in the notes we did it about the x-axis. Well, the y-axis is a lot easier because our y-axis is right through the centroidal axis of each shape. So I don't need to use parallel axis theorem for this one. Instead, I have 1/12. Well, I say 1/12 bh cubed and just say that this is my base. But if you look at the handout, I believe it says 1/12 b cubed h. So you might have those two values flipped, but it's the same idea. Just multiply them together, right? But I have three different shapes. Each shape, like I said, their centroid is already on this axis, so I do not need to use parallel axis theorem. Instead, I'm just using that equation three times, adding it up to give me the 64,256 millimeters to the fourth. For the radius of gyration, k, we said that's just a simple equation. It's the square root of the moment of inertia divided by the area. So I have three areas I add together, divide that into the moment of inertia I found from the first part, take the square root, and I got 8.87 millimeters. The second one, it says, what is the moment of inertia about the centroidal axis? It is symmetric, so I know the centroidal axis is halfway up of each one of these configurations. Now, there's two ways you can do these problems. One way is to use parallel axis theorem. This is the way I did the first one, and I treated these two bars or these two parts of the web as one piece, and in essence, I'm calling those two outside pieces shape 2, meaning since they're both symmetric about that centroidal axis, I don't know, I just have the same equation, so I can just multiply it times 2. So we said the moment of inertia is 1/12 bh cubed. Now this is the x-axis, plus ad squared for my moment of inertia. So for these two flanges, the top and the bottom, that's what I'm doing first. That's why that 2 is right there, because I have two flanges. You could separate those if you wanted. 1/12 bh cubed, 1/12 215 cubed, plus this is my area, and then this is the d. I can see with that d value, I have 150 to get from the centroid down to the top of that flange, and then I have to add another 7.5 to get it to its centroid, giving me that 150 plus 7.5. For my other shape, shape number 1, I don't have to use parallel axis theorem because its centroid is already on that axis, so I'm just using 1/12 bh cubed. Add all that together, and I ended up with 2.1645 times 10 to the 8th millimeters to the fourth. Now, as an alternative, what I could have done, and this is what I did in section B, make it a little easier, what I could have done is said, well, let's just look at as if this whole thing is one big rectangle and find the moment of inertia of that entire rectangle, and then I'll subtract out these two inside pieces. Now, the reason I can do that is because the centroidal axis, for each one of those parts I'm subtracting, is the same as a centroid for that first rectangle. So because all three rectangles, the big outside one and the two colored in red, have the same centroidal axis, I can do that. So that's what I'm doing down here. I have 1/12 bh cubed for the entire big rectangle, and then I subtract out those two red rectangles. So you could do that as well. Either way works. Just be careful. You could not do that if you had like a T shape or something like our last section. And the reason it doesn't work is if I want to know what I would have the centroid of the T shape is like, it's somewhere skewed up towards the top, right? And if I look at so if I did the outside rectangle, then I have the centroid is right at the midpoint. And then if I did these two blue sections, then their centroids are like a little bit, where would they be? They would be, well, I guess it would be about here. I don't know, but it's not the same line, so that's what's screwing everything up on that one. So make sure that it is symmetric if you're going to use that subtraction technique. And so on this last one, we have a non-symmetric I-beam. We have to find the centroid and then find the moment of inertia about the centroid. This is the key problem. This will be like what you could expect on the final, probably the most important part going forward. So the first step, just finding the centroidal axis. I have our equation, sum of our AY divided by our sum of our A's, and that gave me 7.7 inches. Now I decided to go from the top down. I can't exactly remember why that would be any better. You could just as easily go from the bottom up, and if you went from the bottom up, you'd have uh, 20 minus 7.7, which would be 12.3. So either one would work, and it looks like actually it looks like I did both here. So you can compare your answers, either the 12.3 or the 7.7. Either way, you'll get the same moment of inertia. It looks like I'm doing this problem twice to show that. I forgot I did that. Then we're using parallel axis theorem, so we're using this. The moment of inertia is equal to the moment of inertia of each shape plus AD squared for each shape. And the D, so I have it as shape 1 being this top shape. Shape 2, I believe, is that middle shape. And shape 3 is that bottom shape. So if you're trying to follow, let me make this smaller so you can see the whole thing at once. So we can see we have 1/12 BH cubed, 1/12 20 times 4 cubed for that shape number 1, plus the area 20 times 4. Then the hardest part is probably this D value. And what I'm doing is I do 7.2 is the distance to go from the very top to that centroidal distance, and I'm subtracting out the centroid for that shape. So you can almost make that as a general equation where the first one is the centroidal axis, right? Your y bar minus the centroid for that shape. So I've never done that before. That's kind of cool. You could just make that an equation and always use it. Because you're squaring it, doesn't matter what order you're doing it in. And you'll see that I do that with each one. So with the 11 minus 7.7, I know the centroid for that shape 2 is 11 down. I switched the order. You could always do 7.7 minus 11, get the same thing. And then for the last one, its centroid is 19 down. Now I'm guessing most people actually did it this way. Centroid from the bottom up with this 12.3. Same idea, right? So these are my y bar for all three of those. This is all for the D, and then this is the centroid for each one of those shapes. So the same principle still holds true. Yeah, so take a look at that. Watch this again. Slow it down. Pause it if need be. Let me know if you have any questions, and I'll talk to you all later. Thanks. Bye.